The other one was faster. This one's slower, but I also didn't want to like go through my hand.
All right. So NMOS and PMOS. NMOS is good at passing what? And why? So if I'm trying to pass a signal from here, it's a digital signal. NMOS is good at passing what? I know you guys, so that's why I have a quiz today. Just pay attention to it, right? Why? Take a look at it. Does it matter which is S, which is D? Not really. It's symmetrical, right? In that case, whenever I'm having a 0 here, what's going to happen? You have to turn on VG anyway. It's a digital signal, so the gate has to be 5 volts, logic 1, okay? So then here forms a VGS. Either way, just have to satisfy that whatever from G to one of the terminals has to be larger than what? VTHN, right? Doesn't matter which is G, which is D, which is S. Doesn't really matter. So here forms a VGS. So this VGS is 5 volts. Okay? It's great. Looks great. Okay? 5 volts is way larger than VTHN. So if you have a 0 volts here as well, no problem. Okay, until when you are seeing a problem. So when this voltage, if we zoom in here, it's going to be a ramp, right? Like this. Whenever it rises to which point, you are having a problem to pass it. It's going to be VDD minus VTHN, right? It's going to be this. So this little range here has to be VTHN. Why is that? Because your gate to source voltage difference becomes VTHN. Can that be smaller? Whenever it's getting smaller, it's shut it off. So anything higher than what? Anything higher than, so for here, the voltage here, right? Anything higher than VDD minus VTHN, can that get passed through the NMOS? So the NMOS is good at passing zeros, not ones, right? Okay. So for this one, for PMOS, you want to give what kind of voltage to the gate for PMOS? In digital signals, you don't have choices. There's not like 2 volts, 3 volts, right? It's just either ground or 5 volts, or logic 1. Doesn't matter. So sometimes the logic 1 is 5 volts. Sometimes it's 3.3 volts. And for all these low power design, even for the 180, it's not even low power, but still it requires, so the core here in the chip usually is taking in 1.8 volts as a VDD, but however your power supply is still 3.3 volts, so there's a voltage regulator inside the chip to step it down to 1.8 volts to supply power to the core. But all the rest, sometimes the pads have buffer circuits, all these, remember all these pads? These pads are the metal 3 openings on top of the chip. Okay, so all these pads have some buffering circuit in it. So these buffering circuits are getting 3.3 volts. But the thing is, in order to save power of the whole power consumption, so we are step the 3.3 volts down to 1.8 to supply the power to the core. Okay, so the core is taking like only 1.8 volts VDD. So for this one, it doesn't matter. It's 1.8 logic or 3.3 logic or 5 volts logic. It's just either logic 1 or logic 0 for the gates or for the other terminals. Digital circuits doesn't have any intermediate voltages. So for that case, we just ground it. That's the gate, right? That's a gate. It's symmetrical, so it doesn't matter. If we treat this one as source. Okay, whenever we have a 0, it's oscillating, right? Oscillating. So we zoom in this ramp here when it's getting 0 volts, starting from 0 volts. Are we turning this PMOS on or not? What's the requirement to turn it on for PMOS? VSG, right? Yeah, VSG is from S to G instead of G to S as NMOS. So for this one, it has to be VGS larger than VTHN. For PMOS, is VSG larger than VTHP. You'll see VGS, they use VGS for some other textbooks. it's going to be the same. So if you use VGS, the VTHP will be a negative voltage. It will be a negative voltage. So you flip the voltage, the threshold voltage becomes negative. So it's a little bit inconvenient. We don't like it. So in our textbook from Dr. Baker, actually Dr. Jensen is a co-author of that book. Did you see that? Anyway, so he wrote all these C5 layer, all these semiconductor layers chapters, I think. Anyway, so that's why I'm working here, because he introduced me to Dr. Jensen. That's why I got hired 8 years ago. So if you look at the ramp, VSG is larger than VTHP. We're constantly using a positive voltage over here, which is fine, because VSG becomes positive. It's larger than usually this is 0.9 volts. Okay, 0.9 volts. So in that case, if S is 0 volts, what's going to happen? What is our VSG? If S is 0 volts, what is VSG here? 0 volts, right? So it's lower than VTHP. So it's going to shut it off. No current can go through the channel. So in that case, it has to rise to a point. And what is that point? In order to get all the voltages above it pass through the gate. What is the voltage here? VTHP, right? VTHP. I mean, this is voltage here, voltage of the source. So whenever this is larger than this point, which is VTHP, it is able to pass the voltage through the channel. And you can see, since we don't have the intermediate voltages, so in that case, it's good at passing ones. So PMOS is good at passing ones. Okay? Are able to explain this in the quiz? Yeah? All right. Then we can form a circuit by using the features of PMOS and NMOS. We can form a complementary circuit. That's why it's called CMOS. It's complementary MOS. It's not just NMOS or PMOS logic. So we can form a circuit called inverter as a very fundamental logic gate. That's VDD. And that's V in, that's V out. I give you like 10 seconds to draw this schematic on your paper by yourself, since it's going to be on the quiz. I mean, looks pretty simple, right? I'll let you, before you make that mistake, I'm going to just show you that mistake. Hopefully nobody will put it on the quiz. So I've seen this for so many times in the past. Somebody got confused, so I can tell they are very bad at drawing, even worse than me. They do this. If I don't draw this here, I guarantee you there's someone will draw this kind of thing on the paper. Same input, 2 wires connect to the same wire. Why do we need the 2 transistors here though? So keep in mind the 2 gates are shorted. 2 gates are shorted, and the gates are being used as an input. And the drains are shorted together, source are shorted together as well. Oh, sorry, drains. Because this is the drain of the NMOS and the drain of the PMOS. The 2 drains shorted together and form an output. And the PMOS is shorted to VDD, put on the top. So PMOS, keep in mind, PMOS is on top because PMOS is good at passing ones. NMOS is the bottom and shorted to ground because NMOS is good at passing zeros. That is why the complementary MOSFET circuit is being formed this way. All the PMOS are on the top. So if you imagine there's a very big scale, large scale integrated circuits, okay? So usually we split everything in the middle. We don't have like PMOS here, PMOS here, PMOS here, NMOS here, NMOS here, NMOS. No, we split them. So all the NMOSs are on the top and all the PMOSs are at the bottom. And I'm gonna ask you why we are doing that. So there's we don't have to draw a line, right? But it's we just split them. So all the PMOSs are being placed, being organized on the top. So all these are PMOSs. And why do we have to do that? Think about it. What's the reason we are doing that? This could be like millions of transistors, keep in mind. It could be like millions of gates. we haven't learned how to draw the AND gates and NOR gates, but the same thing. So all the PMOS is on top. Doesn't matter if it's inverter or NOR gates, NAND gates, doesn't matter. So, but we place all the PMOSes on the top at the same time, and we organize them the same way on the top. We don't like place them up and down, right? So we organize all the PMOSes on top. So for example, some of the NMOSes doesn't take too much space. Their PMOS is only this small, NMOS is only that small, right? Even though there's a bigger circuit, the PMOSes are like that big and NMOS is that big. So it makes sense that we have a line in the middle, and so they are making connections in the middle for the drain, right? But so if for the inverters, the PMOS and NMOS are tiny. We still have to stretch them and place them really far away from each other and using a metal wire to connect them together. Why do we have to do that? Why not just keeping them closer and like keeping a PMOS here, right? Keeping the PMOS here. So in that case, I can save a lot of space in the middle to draw other circuits. You'll see this a lot in your layout in the lab. You have to understand what's going on here. Remember we learned about one thing, the wells, the body. Okay, so the body, what is the body of the N plus, of the NMOS? Because the answer is in a second, okay? I'm going to repeat this in the semester so you are able to answer this question during the interviews. So, what is the body of the NMOS? You could say P sub. If it's a one well circuit, a one well fabrication. P sub. There's no another well for the NMOS. It's just a P sub. So the body of the NMOS is a P sub. Or sometimes you can say P well, even though there's no well. Okay, the whole wafer we call it a well, even though it's not a well. You can say P sub or P well in the interview. It's okay, either way. Okay, and then you need a tap. What is the tap for the P well? What's the tap for the P well? Are we able to put a metal here and via and then whatever metal one here and wire in order to connect to P sub? No, we don't do that. Okay, what we do is we have a P plus here, which has a higher conductivity, so your metal have a better contact with it and get a wire. So that's how we connect our wire to P sub. And where do we store our P plus or P sub to, or P well? These are just so many different names. P plus, P sub, P well, it's the same thing, okay? So where do we short this P plus to? There are different nodes, but they are same node, same voltage node. So P plus is shorted to where? Where? Yes, right? Sorry, I was trying to give you a different example. Yes, that's right. This is NMOS, right? NMOS is at the bottom, so that's why your body is shorted to ground. Yeah, you have nodes. Yes, great. Thanks. Because you don't want to forward bias the diode here, right? To avoid what? Body effect. Okay. That's the whole story, right? So for the PMOS, so what's the body of the PMOS? What's the body of the PMOS? The body of the PMOS is the NMOS. These are bodies. Oh, that's a bad one. So P sub, right? P sub, what's the body of the PMOS? N well, right? N well. Is there N sub? Nope. Since we are using a P-type substrate, right? It's a P-type substrate. You say, no, I work for Dr. Jessing, so we have N-type substrate. Yeah, which is fine. But for the C5, it's always P sub. It's N well, right? N well. Who has nodes this time? This is shorted to where? VDD, right? short to VDD. So you see in the lab on Thursday, you'll see, hey, you just connected your, let's do this symbol here really quick. You connected your source to ground. Like I ground here. So in that case, body is shorted to here, then everything is grounded. Yeah, I talked about this really quick last time. I'm pretty sure it was a little bit rushing. Let's just review this really quick so you are not getting confused for the lab. Okay, you short your P plus, the P tab, to ground. Now you are supposed to short your N tab to ground to VDD, but why you grounded? Can you ground it? Can you ground it?
Why are you doing this?
Yeah, I mean, are you supposed? Can you ground it at all? Can you ground it at all? Can this happen at all? You are supposed to short the body and the source to the highest potential of the circuit, because PMOS, we just learned PMOS is good at passing once, right? I mean, why in the lab we can ground it?
We use like a negative voltage.
Yeah, it was just a negative voltage, right? So your source and body is still connected to the highest potential of the circuit. You are not forward biasing the diodes, which is fine, you know. So when I'm talking about ground and VDD, we are assuming that ground is the lowest potential in the circuit and VDD is the highest potential in the circuit. However, once ground becomes the highest potential in the circuit, then we should short N well and the source to ground at the same time, because they are the highest available, which is also fine, you know. You just connect this one to a negative voltage. You are still able to draw current from the source to drain. It's fine. That's why you are seeing all these kind of weird connections in the lab and showing the curves like this instead of to the right hand side. Okay, this also works, but normally we just do VDD. Okay, just let you guys know. Grounded, we grounded. Okay, so VDD minus gate, VSG is VDD, which is way larger than VTHP, which is perfect. So we are able to operate this transistor in the saturation region and run current through the channel. So this one should be shorted to VDD normally, and this is grounded. This is also VDD, okay, in digital circuits. So in that case, when you have everything fabricated in the same well for the PMOSes, and you would like to place the big wood for the PMOS in here for all the PMOSes on the top. So this is the top view, right? It's the top view. When they are doing deposition, they are looking from the top and trying to do all the diffusion from the vacuum chamber into the wafer. Okay, it's pretty difficult to control. If you want to form a different shape of the N well, it's probably not a good idea. You just have a very big mask on the top and split it, so the first half will be a huge N well on the top. Okay, you got one N well on the top, so you can place all the PMOSes into the N well. Does that make sense? So all the PMOSes are in the same N well. So this is one PMOS. I got another PMOS, just PMOS by PMOS, and you have the fox in the middle to avoid crosstalk. You know, you have a little fox in the middle, plugins. So I have a lot of PMOSes into the N well. And same here. Okay, all the NMOSes are fabricated into the P sub or the P well, but we don't have a separate P well, so it's just a P sub. That's why we separate them this way. So it's just a universal N well and P well. Okay. So for the inverter, draw this schematic again. V in, V out. And I'm doing a DC sweep. V in, if it's linear, Probably just V, doesn't matter. I mean, just voltage and voltage, voltage versus voltage. V is linear. Why? Because X and Y is the same, right? X and Y are the same. X equals Y. So the V in doing a DC sweep is that plot V in looks like this. So V out looks like what? V out. Whenever it's 0 volts. 0 volts. What's happening for the PMOS? 0 volts. What's happening for the PMOS? On or off? On, right? NMOS on or off? Lower than or higher than VTHN? Lower, because 0 volts, right? What about here? VSG, VDD, right? VDD higher than VTHP. So which is on, which is off? On, off. Okay? So PMOS is on, so it's open up. P channel is open up, so it's gonna pull this terminal up to VDD. It's pulling it up. It's pulling it up. This is off, so there's no current. Okay, so it's like off. You can remove it, disconnect it. So everything happening here is gonna be VL is being put up to VDD. How this is getting put up? No, it's being put up. It's being put up. So the channel is on. It's just some terminals in some terminology in electrical engineering. So when the channel is on, right? So this is being shorted. You can say it's shorted to VDD, or can say this point is put up to VDD. It's because VDD is dumping current into VL. Because dumping current into it, it's dumping a lot of current into that node, and that's why that node is being put up to that voltage. Okay, just keep in mind that's how you describe it, because it's dumping a lot of current to that, and that is why that node is being put up to that voltage node. Right. So in that case, whenever it's here, the VL is high. Right, it's high. Okay, so when V in is increasing, this is getting shut off gradually, and this is being turned on gradually, and this point, whatever being charged up by the VDD previously, okay, usually there are some capacitive load or something else, so it's able to hold that charge. Okay, so it's holding this charge here at VDD, but whenever this is off, this is on, it's going to short this to ground, and because it's dumping current to ground, and that is why this is being put down to ground. Being put down the ground, and that's why this becomes 0. It's like this. Okay, it won't happen immediately because this is gradually shutting off, and this is opening up a little bit. You know, whenever this is rising, V in is rising, and so that's why you are seeing a ramp here. But eventually, whenever V in becomes 5 volts, your VL becomes 0 volts. And there's a little detail about the operation. You know, like what I said in the past, the square law equation told us IDS or S, it doesn't matter, the PMOS or NMOS. So for example, it's NMOS, so IDS equals KPN over 2 and W over L and VGS minus VTHN square, right? Can we control VGS in digital circuits? We can in analog, but in digital, can we control it? Usually, we don't vary it because it's basically just 5 volts VDD to ground. Digital circuits, there's no intermediate values. Just VGS is just, in digital, basically just VDD. Okay, can we control KPN? No, it's from the foundries parameters of the technology. It's mobility of the electrons, and which depends on the doping concentration, I think. So this is not changeable as well. So eventually, the only parameter you can modify is going to be W over L. W over L. So because L is a minimum length, If it's a C5, it's gonna be 600 nanometers, because we usually use 2 lambda as a minimum we can use. So it's a 2 lambda, which is 600 nanometers, and we don't want to change it. We just keep it at a certain length, and we modify W on the top to change the current. In order to change the current, to change what? To change W, to change current. In order to change what? Driving capabilities. So change W to change the current in order to change the driving capabilities. So we don't touch L really. In digital circuits, keep the L as a minimum, so you can reduce the total footprint of the whole circuit. So in that case, we can modify the PMOS and NMOS in order to change a key parameter called switching point. So at this point, what's the relationship between Vin and VL? Yeah. So Vin equals VL, which is called VSP. Switching point. So we can modify switching point for the following reason. Okay? If you have a wider PMOS, we're not talking about length because we don't touch length. Okay, just let's talk about width. So if we make a wider PMOS, are we making that PMOS stronger or weaker? Stronger, because a wider PMOS is going to give a larger current. So a larger current can pull this point up more efficiently. Like I said, when you're dumping current to a node, you're actually pulling that node's voltage up to that VDD if it's shorted to VDD. That makes sense? You dump more current, which means you are stronger, which means you can pull that point up to VDD more efficiently or more quickly. So a wider PMOS is going to give you a stronger PMOS on the top. Okay? And if you have a smaller width for the NMOS at the bottom, so you can imagine, two people, one, for example, Mike Tyson's on the top pulling something on the top, and me is pulling something down. So who is going to pull it up first? Definitely the stronger one on the top, right? So the curve will be different. So at zero, who is pulling? Mike Tyson, yes. Right? Because PMOS is on, NMOS is off. Okay? I was taught not to pull it at all. But whenever it reaches the middle, both of us are pulling. Okay? So in that case, if you have a stronger PMOS on the top, it's going to holding that one for longer or shorter. It's not a time, but whenever Vin is changing, your PMOS is able to hold the one for longer or shorter if the PMOS is stronger. It's going to be this, right? Because it's so strong. When Vin increases, even though it's trying to shut it off, right? Because when Vin increases, the PMOS is so strong, it refuses to be shut off. So it's going to keep on for a little bit, okay? Until a certain point, it will drop. So in that case, the switching point will be shifted to the right-hand side. Okay? So for digital circuits, it's a 5 volts logic. We prefer to keep the switching point at 2.5. It's right in the middle. So anything lower than 2.5 can be considered as logic 0. And anything higher than 2.5, for example, you give a... Okay, that's another thing you need to know. So for example, you are using a 5 volts logic, like Arduinos, right? You're having a ESP, which is 0.3 volts. are thinking, hey, can I communicate between ESP and Arduino? Probably the Arduino's digital logic will fry this chip because this guy cannot handle anything higher than 3.3 volts. That's true. So you have to use a voltage divider for the signal from here to here. Okay, you have to divide it. How do you divide it? You have to use a resistor string like this. So here's a 5 volts logic, and you're getting a 3.3 volts logic output on the other side, and this one getting input into the ESP. Okay, so in that direction you have to divide it. But in that direction, do I have to do anything? Do I have to do anything from here to here? Like I'm sending a 0, 1, 0, 1 digital signal. Like 3.3 volts has 1, 0 as ground as 0, and so they have a common ground definitely. And I'm trying to send this signal from ESP to Arduino. Can I do that? Do I need a voltage something divider to protect it? No. Why? Definitely it's lower than 5 volts. It doesn't have to protect it. But the thing is, 3.3 volts logic high can be treated as a logic 1 for the 5 volts logic circuits because it's higher than 2.5 volts. Okay, so 3.3 volts will be treated as logic 1. Okay, because you don't have intermediate voltage values. So one direction from ESP to Arduino is okay, but for the other direction, because a lot of times the communication are bidirectional, right? Like all these TX and RX for UART, SPI, I2C, whatever. So they are all bidirectional. So in that case, whenever it's a transmitter node to a receiver node to the ESP, you need a voltage divider in the middle. Keep in mind, otherwise it's going to damage the ESP in a second. Whenever you part it on, done. Make sense? Okay. Question on this? Let's run the simulation and look at it just real quick. So it's a good chance to show you how to do it, even though it takes probably 5 minutes, but it's worth it. So first you need to grab, even though this is LT SPI, it's not electric VLSI, but it's very similar. So you need the PMOS 4 terminals. Why 4 terminals? Why 4 terminals for the PMOS? Include the body, right? The body. So the body contact. Let me ask you one more time. Okay? This node, N plus or P plus? N plus or P plus? No. This is the body contact for the PMOS. N plus or P plus? N plus. Why? Because it's N type. Why is it N type? Because PMOS is in N well. Okay? Can I change the width and length? Yes, right click. Length, 1 micron, just make it big. 2 micron for the width. It's not showing, control right click. Check this mark to display it. Right click, 1 micron, 2 micron. Control right click. Check the mark and to display it. So NMOS and PMOS, for the name of the transistors, they are fine because in the C5 model, you can see the model file from the manufacturer. I think this is a simplified version of it. Defines all the physics parameters. You can see the name of the model is called NMOS, so we don't have to change it. So let's just call it NMOS, PMOS and NMOS. And we need a power supplies, of course, because we need to turn them on and do the DC sweep. So the first one, let's just call it VDD, give it 5 volts. And I'm gonna connect the net here to the top and ground it. So this is the power supply. And I'm going to duplicate VDD and put it to PMOS, which makes sense because PMOS source is shorted to VDD, and I want to short the N plus of the PMOS or the N tab to VDD as well, so I can directly duplicate it. Make sense? And for ground, I can just ground NMOS and ground the P sub, which is the body contact, the P sub. So is it N plus or P plus here? P plus, because it's the P tab. Okay. So these are the gates, 2 gates, okay, 2 gates. And I'm gonna name as V in, ground. And I'm gonna copy V in to input, and I'll do a V out so I can probe it. Okay, and you should be able to drag this a little bit. No, you cannot. Let me just put it here. So that's V out. And so what I can do is, for DC sweep, I don't really care about the value. I just give a 0 volts for V in, because I have to sweep it anyway. And this I just call it VGS, since I'm doing a DC sweep for VGS. So for DC, it's called DC analysis or DC sweep. Keep in mind. Let's just call it DC sweep. So it's gonna be .dc, and I'm sweeping VGS, okay, from 0 to 5 volts, and I'm gonna draw a point every single 0.01 volt. Okay, that's a DC sweep. So there's no time. So x-axis will be voltage and y-axis will be voltage as well, since we are going to probe it. And let's we have to include the model file. So you can right-click this spice commands and click this button and Control-Enter. So it's switching a line instead of closing that window, and do a .include. You'll see this spice code in the lab tomorrow as well. So it's gonna be C5 underscore models.txt. And because I do have the same file in the same directory, so I'm gonna save this one to desktop because of that reason. Since I have, if you see I don't have it there. So I'm gonna just do this draft 1. Okay, so you can see this is being saved as draft 1. It's the same directory as the C5 models, and now I'm gonna run it. Okay, V in is a linear curve because I'm just sweeping V in. It's on the x-axis, but because I'm plotting y as well. So in this curve, what is the y-axis? Yeah, y-axis is also V in because a linear curve is y equals x. That is why when you are sweeping V in on the x-axis, it's going to show a linear curve like this, which means y-axis will be V in as well, before we adding any other voltages to it. Okay, then I'm going to probe V out, so it's plotting V out in the same curve, and it's switching at this point. So what's the switching point for this design, for the inverter design here? It's about 2.1 volts. I can definitely put a cursor here and try to probe it. Right? 2.07 volts. Okay? Is that ideal? Probably not. Okay, so I want to make the switching point exactly at 2.5 volts. What should I do? There will be some calculation. We'll cover that on Friday. But what should I do just roughly? Which one should be stronger? PMOS should be stronger, so we should place Mike Tyson there, okay, instead of someone else. Okay, so in that case, we want to change what? Width to where? Just let me know. Yeah, more like 3, for example. Okay, 3 micron. Let's try it. Still not there yet. 4. Close. 5. Over 2.5 already, but I think should be 4, roughly 4. You know why? They are both transistors from the same technology. Why PMOS just requires larger width? Why is that? Yes, because holes are less mobile than electrons. Okay, so in that case, we need a wider, a stronger. So eventually, they are actually PMOS is not. I don't want to say it's stronger. It's just they are pretty much the same strength over here right now. We just need a wider PMOS because the mobility of the holes are less than the mobility of the electrons. That is why. So you can modify the width in order to reach that desired switching point for the NMOS. And let me take a look at this really quick, see if we have everything covered for the quiz. We did. Any question on this? Anything I missed? You know what? I just let you guys do the quiz since I'm just so lazy.